Hello everyone, welcome to back to our advanced material series. I am Dr. K. Nehru from Aerospace Engineering, and today we will explore one of the most elegant concept in analytics dynamics, that is Hamilton principle and Lagrange's equation, which is express the vibration phenomena in the mechanical system. Instead of focusing on focus directly, analytical mechanics are used to energy and various principles to describe motions. The powerful framework for this foundation of modern physics, aerospace engineering, robotics, quantum mechanics, and even Einstein theory of relativity. They are incorporating this kind of equation, especially in the analytics dynamics, especially in the vibration area of vibration. We can understand how the Hamilton principles uses in different applications. By the end of the session, you will be able to understand Hamilton principle and the concept of action in classical mechanics. We'll learn how Euler equation, Lagrange equation are derived and applied on the determined equation of motion. We will explore generalized coordinates and see how the simplified systems with multiple constraints. We'll also study real engineering applications in aerospace, robotics, and mechanics system. Finally, we'll compare Newtonite, Lagrange's and Hamilton's formulation to appreciate the power of analytics mechanics used in the vibrating systems. Let us brief looks at the history evolved on analytical mechanics in 1788. The great mathematician and physicist Joseph Louis Lagrange published an antiquity introducing a revolutionary energy-based approach to mechanics. Several decades later, William Ruff Hamilton's formula, Hamilton's principle, excited variation ideas into a more general framework. In 1835, Hamilton's mechanics had evolved into a conical equation that continued to influence modern science. The more remarkable insight is the variation principle connected classical mechanics, optics, quantum mechanics, and field theory under a unified mathematical language. Today, this idea remains center of aerospace engineering, computational physics, and advanced control systems. Now, understand the core concept. Hamilton principle states that the actual path followed by a mathematical system makes the action integral stationary. The action is defined as S equal the integral of Lagrange's over time. Mathematically, S equals to integral of length rate of time dt. The variation of action is 0. Delta S equals 0. The Lagrange itself is given by L equals T minus V, where T represents kinetic energy and V represents the potential energy. Applying the principle of variation calculus leads to famous Euler Lagrange equation d by dt for a partial L with respect to q dot minus partial L with respect to the q is equal to 0. This equation provides the equation of motion for a system with generalized coordinates. This approach becomes incredibly powerful when dealing with constrained or multi-body systems. For a mathematical formulation key concept, let's dive deeper into the mathematical foundation. For every generated coordinate system, Q is suffixed to I, which obtain the one Euler Lagrange equation. The term partial differential of L by partial with respect to the Q dot represents the generated moment, usually denoted by P suffix I. The term partial L by partial Q, dou Q by dou L by dou Q represent to generalized forces. For a system which n degree of freedom, we obtain n second order differential equation. This kinetic energy represent as T equal of m minus v square. This depends on generalized velocity and often leads to formation of mass matrix. Potential energy depends only on positional coordinates and representing the convective forces. Lagrange's combine these two equations provides a compact and the elegant description for the system dynamics. This framework dramatically simplified complex engineering problem compared to the traditional force-based approach, help us to understand the formation of mathematical equation. Coming to the applications of Hamilton principle in physics and engineering, which is numerous scientific and several applications. In astronomy, it helps to analyze planetary motion, satellite trajectory, and gravity interaction in n-body systems. In aerospace engineering, Lagrange mechanism used to aircraft dynamics, spacecraft altitude control, missile guidance, and rotor analysis. Robotics extensively relies on generalized coordinates to model robotics multiplication, motion planning, and the automated control system. Other important application includes double pendulum, coupled oscillation, structural vibration analysis, earthquake engineering. Perhaps most profoundly, Hamilton principles form the conceptual foundation of quantum mechanics through Fermi path integral formulation. The same mathematical idea continues to shape our understanding of both microscopic and cosmic phenomena. Coming to the concept, mind mapping, Hamilton keeps in the center the Euler equation, action integral equation, energy foundation, all coupling together gives the various application of Hamilton principle. Energy function remains that Lagrange equals to kinetic energy, which minus of potential energy. Finally, constrain whether the non-harmonic and harmonic defines the permissible motion of the physical system. This concept creates one of the most elegant structures in the theoretical physics. Let us conclude by today's session. Hamilton principle teaches the nature follows path by stationary action rather than the simple responding to the force. Lagrange equation provides a powerful alternative to Newton's law, especially for the system with multiple degree of freedom and constraint. Generalized coordinates allows engineers to model complex systems and more efficient. Applications span aerospace engineering, robotics and structural dynamics, astronomy and quantum mechanics. Uses the design thinking framework. We move through empathy to the testing, which is the variation principle underlying much of modern physics and engineering into the single elegant mathematical language. Thank you for joining this exploration into the advanced mechanics used in the vibration. If you enjoyed this lecture, please like, share and subscribe for more aerospace and engineering concepts. Thank you. We'll see you in the next class.